Well, hello, everybody. Thank you for attending this session. Today, we'll be talking about integrating with complex messages and data lake archives. I'm Ryan. I'm a technical lead at Vertica on some development teams. I lead the execution engine and complex types development teams. Today's talk will begin with an introduction to complex data types, what they are, why you might want them, and where you might find them. Then we'll take a look at the different ways to use complex types in Vertica and some technical details about how things work under the surface. We'll evaluate the claims that we'll make in the introduction and offer some recommendations. And then we'll look ahead to what will be available in version 12.0 and beyond. So let's get started. I always like to start with some examples. Here we'll look at three flavors of complex type: row, array, and map. A row type is a list of named fields. Sometimes these would be called struct, especially if you're using an imperative programming language. Our example here, customer, is a row type that has two fields, a varchar field named name and an integer field ID. Next on our slide is the array type, which is a collection of homogeneously typed elements. Here, ship dates is an array of the date type. Values of ship dates contain 0 or more date elements. Our third complex type is the map type. This type is a collection of key value pairs. Our HTTP requests example maps varchar keys to varchar values, such as things you might find in an HTTP request header. Keys could be things like pragma, host, or request. One thing to note about the map type is that an implementation could treat it like an array type with a complex row element of two fields, key and value. The examples from the previous slide all had non-complex types as fields or elements, but we can nest complex types too. This example nests complex types within complex types. Web sales values represent individual online orders. This type has a customer key field, a collection of the items that were ordered, a set of fields tracking the pages that the customer visited and how much time they spent on each, and then finally a ship date for when the order was shipped to the customer. Now, why would you use complex types? One of the key benefits is the co-location of related data in the same row, which lets you take advantage of locality. This example schema on the right pairs usernames with search terms. Using the traditional relational model, you'd probably set up a table with one row per search term. Queries to this traditional schema might require you to normalize your data and join this table with other tables. Storage of this traditional schema is probably going to duplicate the username for each search term. But if you use complex types, then you can avoid joins and avoid data duplication. Another reason to use complex types, they're a natural fit for data which comes from other domains which already support complex types. NoSQL and imperative programming languages like Python all use complex data natively, and it's just easier to work with this data in SQL if you don't have to do a bunch of pre-processing to flatten the fields or denormalize collection elements. A complex map type is also a great fit for sparse data or unstructured data, where some keys are present just some of the time, or sometimes new keys will just show up. This is something that might happen with HTTP requests in Web 2.0 applications. Complex data types can also make it easier to write, read, and analyze queries. A query with fewer joins and aggregations is just easier to deal with. And it probably is also going to have a simpler execution plan inside the database. And we'll see examples of that in short order. So first, let's look at this locality benefit more. Queries that can exploit locality can benefit from complex types. Clickstream or search applications, for example, often have a set of data that's associated with each row, and common queries do things like count the number of values, such as search terms, for each user, or find users that have a certain property, such as which users searched for a particular term. A traditional schema here, words flat, keeps one row per search term. The complex schema, words set, instead keeps one row per user, with all of the search terms for that user collected within the set type column words. The set type is like the array type, but each element in the collection is unique. Let's compare how we might ask the same question to these two different schemata. Suppose we want to count the number of distinct search terms per user. With a traditional flattened schema, we have a query that uses distinct and has a group by. But with the complex type schema, we don't have either of those. We can just use the apply count function instead. Since we have a set type, the terms are already distinct, so we don't have to group by anything. There's just one row per user already. A question to find users with particular search terms leads us to more similar queries for each schema. We just end up with a different predicate. This is an equality predicate for the flattened schema, and on the complex type schema, we can use the contains function to look up whether or not the set of words contains the search term. Users that do have a match might give us results faster, since the contains function doesn't have to look at all of the rows for that user. Those examples give us an idea about how we can benefit from data locality, but let's look at an example now that uses complex types to avoid joins. This example shows two different schemata which describe the earlier web sales example. The traditional normalized schema uses three tables. The web sales table has one row per sale or session. The orders table has one row per item in a sale. And the page counters table has one row per page visited in a session. With complex types, though, we can use just one table to represent all of these, neatly packing the orders and page views into array types. For our query of interest, let's ask which pages are the most interesting to our best customers and when. Where did our customers who ordered more than 5 items spend their time? With the traditional normalized schema, that query looks like this. We join page counters with itself, and then join that with each of the other tables. It takes a bit to soak in this full slide's worth of SQL. Unsurprisingly, the full slide's worth of SQL leads to a full slide's worth of query plan within the database. In addition to the joins, we have to materialize data from 3 different tables and do aggregation on the orders table to identify the sessions with more than 5 items. In contrast, with the complex type schema, we can fit both the query and the query plan on the same slide. There's no need to do any joins, and instead of group by clauses, we have the apply count, apply max, and array find, and array index operator to turn everything into just a couple scalar expressions that's easy for the query processor to understand. And indeed, the query plan is just 2 steps. One, to evaluate the apply count predicate and materialize data, and another to evaluate the scalar expression. If we're using a native table, as opposed to an external table, then we reap the additional reward of having the predicate pushed down to the table scan, where we can leverage the traditional database optimization. Don't materialize other columns for rows that don't pass the predicate. Moving ahead, let's take a look at where we can find complex types. There's a bunch of formats that are commonly used that support them. JSON leads the charge. JSON is an unstructured, text-based, self-describing data format. Each record defines its own fields. Arrays and objects, or maps, are primitives in JSON and can be arbitrarily nested within each other. Another popular format is Avro. Unlike JSON, it's a structured binary format. Each file adheres to a fixed schema. And in addition to row, array, and map types, Avro also has enum types and union types. Also very common are the binary formats ORC and Parquet. Unlike Avro, these formats orient their data in a columnar fashion, so they have special encodings for their complex data types. The ORC format's encoding is similar to the design that we ended up implementing within Vertica. This table offers a quick guide to what's supported differently across the 4 formats. JSON is the unique, unstructured, non-binary format, and Avro is row-oriented in contrast to ORC and Parquet. Background covered, let's take a look at how we can work with complex types in Vertica. Well, first, where do you start? Probably you should start with the data itself. Someone's giving you data, you got to put it in your database. Makes sense. These days, JSON is pretty hot, so let's use that as our motivating example. JSON, as we said earlier, is a self-describing data format. There's no fixed schema. So if we get a JSON file on the slide, it's not really obvious how we're going to turn this file into a complex type table. There's 2 restaurant records here, and they have slightly different schemata. The second record has an extra key capacity for its location data, and it has an entire events key that doesn't appear in the first record. And we don't really know what other records that don't fit on this slide could possibly have. One place we could start exploring our data would be to use flexible complex types, which have been a Vertica feature for years via flex tables. Flexible complex types share a lot in common with JSON. They encode the data as a row-oriented, self-describing key value pairs. Sounds like JSON. These types are great if you want to explore or if you value flexibility more than you value performance. When you load data into a flex table, the data parser will write all of the data's key value pairs into the special raw column. Once your data is in your table, you can use a suite of vmap functions to explore it. For example, the map keys function returns a table of the keys that appear in each row, and the map to string function turns the vmap value into a human-readable text representation. If you identify columns within the vmap that you want to promote to named columns of your table, then you can use alter table to do so. You can do this to promote a simple key, like name in our example, is just a varchar column, or you could promote a complex key into another flexible complex type by adding it as a long var binary column, such as the menu in our example. The alternative to flexible complex types is to use strong complex types. With these types, you write clearly and specifically what your types are. You write down the arrays and rows, you write down the elements and the fields of each. If you do this, Vertica will store the data in a native format, which is definitely going to make your queries run faster than the flexible alternative. You'll also gain some analytical capabilities, which we'll discuss next. But how do you start? If you're looking at a JSON file with thousands of records, it's quite a daunting task to pick out what the schema actually is, especially if the data is deeply nested. Well, good news. Vertica has a function named infer table DDL, which will scan the file and do a lot of that work for you. It reads the contents and spits out some recommendations for table definitions. You can pick one of those table definitions, tweak it to your needs, and then run that in your database, and now you have an external table or native table that matches the data that you have. Whether you choose an external table or a native table, one of the key functions that you can use with strong complex types is the explode function. Explode is a transform function which turns an array column into a new table with one row for each array element. This function is critical if you need to do just about anything with your array elements. Another advantage of strong complex types comes via the export to JSON utility. With this, you can turn any query result into a JSON file or a set of JSON files. You can import these files into another table, another database, or any other analytical platform that supports JSON. Yet another advantage of strong complex types is that they cover other use cases too. For data science and machine learning, we might want an intuitive way to represent matrix data inside our database. Matrices map very well onto two-dimensional array columns. You can even include the number of rows and number of columns. This is a good practice in all situations, since it tightens the column size, which should improve memory usage and performance of queries and data loads. In this example, we have a 3x2 matrix, and so we turn that into a two-dimensional array with 3 elements of the inner array and 2 elements in the outer array. Strong complex types are also well supported by Vertica's SDK. We've built support for complex types into our C++ and Python APIs so that you can write all kinds of custom functions to operate on complex data. The example here is a matrix multiplication function written in Python to process two-dimensional arrays of integers. But what if you want the benefits of strong complex types, but your data doesn't fit all that well? If your data is in Parquet, JSON, or Avro, then you can create a table that uses both strong and flexible complex types. The parsers for these formats can encode specific keys in the data as a single VMAP column. If we go back to our restaurants example, we could imagine that the events data could have a lot of different custom keys depending on what the event is. With that in mind, we can create our restaurants table to use strong column types for the locations and menu, which are probably always going to be the same, and a flexible long var binary column for the events field, which we can then explore using the same VMAP functions that we saw previously. Now, let's take a look at a few details as to how complex types fit into the Vertica data pipeline. We'll start with how complex types look within the query engine. When you query a complex type column, the result that we format and send to the client is, in most cases, a JSON formatted string. But within the query engine, we represent the complex data very differently. Vertica materializes complex data in a column-oriented binary format. This columnar representation fits seamlessly into the query engine that Vertica's always had, enabling queries with complex types to get the same great performance and optimizations that a query that has never had complex data would. This columnar representation has columns for both structure data and value data. For a row type, each field is its own column. We also have a structure column to indicate for each row whether the complex value is null. This allows a null row value to be distinct from a row value that has all null fields. In this example, we have a row with 2 fields, ID and name, So we'll end up with 3 columns inside the query engine. For an array type, we keep structure columns for each dimension, and then one values edge, which packs all of the array elements together. The dimension structure columns include a null indicator column and a sub-array offsets column. The null indicator is itself an array, and it marks whether each array element is null. The offsets column encodes the way that the values of the multidimensional array logically belong to the inner array elements. The array values themselves have a data edge to their own. The values across all array dimensions are packed together. This representation is compact when there are a lot of null or empty arrays. The columnar aspect of this representation is very important for query performance. When you run a query on a complex type column, we only materialize the required fields. If you select just one field of your row type, such as selecting just the ID field of this customer type, then we're only going to materialize ID. We can skip reading name or the null indicator. If you run select count on your complex type, then we don't need to read any of the fields. We can just read what the structure is null column. Now, we've alluded to the set type in some of our examples. The set type is similar to the array type, but it internally sorts its elements so that you can do faster lookups. If you search an array type for a value, then you have to scan each element. But if you search a set, then you can exploit that internal sortedness to avoid looking at each element and getting faster lookup. One final technical detail. The JDBC driver offers native complex type support. By default, a complex query result is sent to the client as a JSON formatted string, but with JDBC, you can request a binary representation instead, and then use the Java standard functions getArray and getObject to inspect your results. All right, now let's take a look at some performance. Let's look at the claims that we made in the introduction. First, let's look at our flattened data versus complex data example. We built a small benchmark to evaluate our claim that complex data will perform better when it can take advantage of locality. We set up tables with user IDs and search terms searched by each user. In our data set, we have 1 million users, each with up to 1,000 distinct search terms. We ran our query on a 4-node Vertica cluster with the tables segmented on the username. We ran our benchmark with 3 different tables. First, words flat, the traditional table where we have 1 row per search term. Then words array, where we have 1 row per user with all of the search terms for that user packed into an array column. And then words set, which is similar to the array table, but we use a set type instead of an array type. The 2 queries that we used in this evaluation are the same as those we used as motivating examples in the introduction. Our first query counts the number of search terms searched up by each user, and our second finds users that searched for a specific term. We ran the queries and normalized the performance results to the performance of the traditional non-complex schema. Both the array and set tables took just 20% of the time to execute on our first query and less than 50% of the time on the second query. In both cases, the sortedness of the set type gave it a slight edge over the array type. We also claimed that complex types would use less space. So, once again, we compared against the flat traditional schema. The array and set tables both use just 80% of the storage space in comparison. Next, let's take a look at our claims about normalized data compared to complex types. We built a benchmark upon the web sales schema that we used as an example in the introduction. Our data set had 100 million sessions, each having up to 10 items ordered and up to 10 pages viewed. We stored this data in Parquet on HDFS and created external tables to query that data. Here's a reminder of our schemata and query. The traditional non-complex schema has 3 tables. The complex type schema has just 1, with array fields instead. For our query, we're asking for the pages where users who ordered more than 5 items in a session spent the most time. This big pile of SQL is how we implement that question against the traditional 3-table schema. And as a reminder, this much smaller query is how we would implement this question against the complex types table. Comparing the performance of the respective queries, the complex types version runs about 25% faster. That's a pretty nice improvement. But the complex types query requires less than 1% of the memory that the non-complex query does, because we don't have joins and we don't have an aggregation. And that is a result that you definitely cannot ignore. So, should you use complex types? If you can benefit from locality or data denormalization, or reduce the size of your table storage, then our benchmarks say yes. Complex types could also be worth it just if you need to simplify your queries. Some other things to consider when using complex types: you should use array bounds to help Vertica's query planner with resource estimation. And you should use set types to get a little extra performance if the element order is unimportant. There is one lingering question. Should you use an external table or a native table? That depends a lot on your data format and your workload. We took the data from the web sales schema in the previous benchmark and compared its performance in external versus native tables. This figure stacks up the total end-to-end latency of creating the table, loading the data, and then running our benchmark query one time. We did this for both JSON and Parquet. In both cases, the native tables have to pay the high cost of an initial load. So if you run the query just once, they might not be the best choice. For JSON, it pays off significantly if you run the query just one other time. Whereas for Parquet, the external table query was only about 40% slower than the query against the corresponding native table. So in this setup, it takes 25 queries for the native table to pay off. But this calculus will change as we make improvements to load times in the future. But for now, we're in the present. So let's take a look at the complex type features that will be available in Vertica 12. First, we've already seen quite a few of the in-database analytical capabilities: external tables, native tables, the explode function to turn an array value into a table of the array's element, full SDK support in C++ and Python so you can write custom functions. We have a bunch of external integrations, such as the JSON export that we saw. There's also some limited Kafka export support with one-dimensional arrays and limited Parquet export support with one-dimensional arrays. And there's also full JDBC client driver support. We have great support for these 4 data formats: Parquet, ORC, JSON, and Avro. You can load complex data from these formats into either native or external tables, and each of them is supported by the infer table DDL function. So you can look at a file and then spit out a table definition. Or if you like, you can explore the data first using flexible complex types with each of these formats. That's going to be version 12. What's coming next? Some of our future work is already in progress, but some of it's still in the early stages of planning. What we intend to do now might change, so the plans that I'm going to show next aren't a commitment. But today, we're thinking about handling schema evolution. How do you integrate changes into your table definition? Improvements to flexible complex types are likely to be part of that story. We're also going to continue improving our in-database analytics, including the explode function. One thing we have in mind is to add some new syntax to make it more user-friendly. Performance improvements are something we always hope to do, and one way we might get there for Parquet files is a possible integration with Iceberg or Delta Lake. Complex types are a great tool. I'm excited for where we are and for what we're going to build next.